Okay, guys, this is the Algebra 2 Honors review video. Just before we get started, I want to go over something on the project. So, just a heads up, a reminder: project is going to be due day 1 of next week. This is the project. Follow the instructions, answer the questions to the best of your ability. Check with me if you need help. When you get to the log portion, you read the supplemental reading, you go back to the data set I shared with you, and you use the log data as your new L2, if that makes sense. So you keep L1 the same, like the explanatory variables the same, you change L2, and you do your, you do the log, what's called the log transformation, and you do the same thing. This would be like another scatter plot with a least square regression line here, and then the new residual plot here, okay? Same thing, then you'll talk about R and R squared. On the last part here, these practice questions, on this one, just to give you some clarity, you will not use any of this or any of this or any of this. You'll just look at these three numbers here. This coefficient, this is going to be your y-intercept. That's the constant coefficient. This is your slope, right? The wind velocity coefficient, that's your slope. And then you do not need to worry about letter D, rather, okay? So just note that. Just look at these three values and then ignore D. Okay, now we can get on with the practice quiz. Okay, so there's a lot of calculator syntax you need to know. Well, a fair amount. These two have to do with univariate data, so when you're just dealing with like one kind of data that, at a time. The first one is just when you want to find like the mean, median, the different quartiles, etc., standard deviation. To do that, you are going to put the data into L1. So I wrote it down here, but I'm just going to do it just to show you. So let's say your data was 8, 6, 5. Okay, you put it into L1. Let's stat edit. Just put it in L1. Then you go to stat calc. One of our stats, we want to do L1. Don't worry about frequency list. Calculate. That's it. That gives you mean, standard deviation, etc. Okay. For normal CDF, this is when you are given like a mean and a standard deviation, and you're looking for like a percentage or a proportion of the data that lies between two values. To solve that, you're going to go to second vars, that's distribution, and then normal CDF. And here, you see this mu and that sigma. Those are symbols also they mean mean and standard deviation. So I know it's confusing, but that mu, that means population mean, which for this class really is the same as x, what's called x bar, which is the sample mean. So you see that mu, that is mean, and then this lowercase sigma, that is standard deviation, okay? S also can be standard deviation, okay? That's for sample. But this, for what we did, we didn't really distinguish too much between population and sample. So really, seeing a mu or x bar is mean, and seeing an S or lowercase sigma is standard deviation. And that's all you know, okay? You don't need to distinguish them. Just know that these symbols mean standard deviation, these symbols mean mean, okay? So we put in our data and we enter the values. So let's say we want to find 20 and 30 with these features. So my lower would be 20, my upper would be 40. So my mu, again, that's really the mean, that's gonna be 30, and then standard deviation, 7, sigma, paste, enter. So this is saying that 84.7% of the data is between 20 and 30. That's how you read that. If you ever had to say like greater than a value or less than a value, you would do the same thing. So second distribute, normal CDF. But if I said like greater than 20, but you didn't put like an upper bound, you said greater than 20, you just replace that with 99999 as the upper bound. If you said less than 40, you would put 40 on top and then just make this negative 9999. So if it ever just says like greater than a number or less than a number, that's when you put as your either upper bound or lower bound 99999 or negative 9999. Okay, just like a really, really big number. Okay, all right, so that's it for univariate. For bivariate, this is the regression. So this is where we're finding that line of best fit, that's the least square regression line, to make predictions about a data set. So to do that, we go to stat, edit, and we have two lists. So I made up a data set here, but you're gonna put something in for L1 and something else for L2, and make sure they're in the same order. So make sure it's like the corresponding values go in each row. Okay. Then we'll go to stat, calc, and then it's linreg down here. And then we did L1, L2, so we're gonna leave that as it is. And then for store, we can use, this is a shortcut, you don't have to do this, but it's helpful. If you do alpha trace, then y1, that will put your linear regression equation in for y1, so it'll graph it for you. And we click calculate, and then that will get us everything we need. So our A, our B, our R squared, and our R are all there. Okay. After you do that and you want to graph it, we can go to stat plot and make sure that this is on. So second y equals, go to plot 1, make sure it's on, make sure it's a scatter plot, and make sure it's L1 and then it's L2 in this case. So that's the columns that we were, the list that we were using. And then we'll click, go to home and then zoom 9. So zoom 9 is going to bring up that scatter plot and put that line of best fit that's stored here because I told it to when we did the section above. Okay, so this is your scatter plot. If you want to do the residual plot, you would do, you would go to stat, then edit, and you're going to go to L3 right here. So you're going to highlight L3. And here, you're going to click second stat, and then you're going to put residual and enter. So what that's going to give you is the residual values for these predictions. So how far off you were, right? So actual minus predicted. So this was 0.5 difference. So an underestimate. This is 1.5 overestimate. This is 1 underestimate. Okay. To plot these, so to plot the residual plot, you go back to stat plot, you turn it on, and then you just change your Y list to L3. Okay. Then you do zoom 9. That's it. So this is our residual plot. And if you kind of want to see the values, if you click trace, you can use that to sort of to see what values we have. So this is 8 and 0.5. That is 6 and 1.5. That is 5 and 1. So just by clicking left and right, you can go through the points and see what values they are, and that helps you graph it. Okay. All right, so that's all the calculator skills. Not too bad, right? Not too bad. These here are the sentence frames. So when we were trying to explain the y-intercept, the slope, and the r squared, this is what you want to say, what you want to use. Okay. All right, let's do the practice quiz now. So, okay, first section is on univariate data. Again, it's dealing with one data type at a time. Okay, so first question, you're given some information. The distribution of scores in a recent test fall closely to normal distribution. Okay, that's key. With a mean of 22 and a standard deviation of 4. So this is all information I need to know. You want to, from this point, draw the density curve. So this is the normal distribution density curve. And right in the middle goes the mean. Right in the middle is going to go 22. Okay. And so the first question says, what proportion of students scored at least 26? So 26 is over here. And at least, okay, that means that amount or greater. So this is the region I'm shading. Now, in this case, you could use empirical rule. Why is that? Well, empirical rule works when we're dealing with standard deviations like 1, 2, 3, -1, -3. And you can see, because the standard deviation is 4, this 26 is 1 standard deviation away from the mean. So we could use the empirical rule to do this. However, you can also just use the calculator, and that's the method I'm going to go over right now. So if I want to say a greater than 26, this is going to be second distribution, normal CDF. The lower bound is going to be 26. The upper bound is going to be 99999. The mean is 22. The standard deviation is 4. Paste. That's it. So roughly 15.9%. Okay? So 15.9%. What is the z-score for a student who scored 26? So the formula for z-score is z equals this is the int symbols. But really this means the value minus the mean over standard deviation. Okay, so in this case, the value is 26, the mean was 22, and standard deviation was 4. That's 4 over 4, that's 1. And that's what I was talking about here with the plus 1. Okay, so z-score is 1. Z-score is the number of standard deviations away from the mean. Okay, what proportion score between 12 and 32? Same thing here. Second, bars, normal CDF. 22 is going to be my, 12 is my lower, 32 is my upper. The mean and standard deviation same. And it is 98.8%. Okay. Okay, good on that. So this is z-score, so understanding the number of standard deviations away we are from the mean and how to figure out what percentage of the data is between certain z-scores. The higher the z-score, the more standard deviations you are away from the mean, the more obscure that data point is. The more data that's encapsulated between those standard deviations because you're further out from the mean, right? So when you're not many standard deviations away from the mean, you're not that weird, but if you're talking about like a quarter of a standard deviation away from the mean, that's not a whole lot of data. But as we go 1 standard deviation out from the mean, 2, you're getting more of that data set. Okay. This one is you're creating a histogram. You can create a histogram on your calculator, but that was not I didn't ever teach you that. Some of you figured it out. I just want you to do this by hand. So to do this by hand, you're just going to count the buckets. So we have first the 50 to 54 bucket. So I'm just going to look through for any of the values between 50 to 54. Let's see, well, 53, that's going to be 1. Okay, it's just 1. So that would be 1. 55 to 59, that's going to be 1, 2. Oh, it's in order, so that's it too. Okay, 60 to 64, 1, 2. Okay, 65 to 69, 1, 2, 3, 4. 1, 2, 3, 4. 70 to 74, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12. 75 to 79, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 84, 1, 2, 3. 3. Okay. So over here I'm going to mark 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's going to be 1. It's going to be at 2. It's also going to be at 2. It's going to be at 4. It's going to be at 12, so all the way to the top. This next one's going to be at 10, so I'm going to mark that. And then this one's going to be at 3. Okay, so doot. Okay, it's my histogram. Not perfect, but that's totally fine. Count the number that fall in each bucket, and then draw appropriately. Let's describe the distribution. So it's skewed left. So I mean, I can go over that again briefly, but basically you have this is symmetric. That's skewed right. That's skewed left. Okay, so this is symmetric. This is skewed right. This is skewed left. And I know that's a little confusing because, make that a little more extreme. You call this having a long tail. Basically, in skewed right, I know you might be thinking, oh, but the data is over here on the left. Isn't it skewed left? No, the center of the data is kind of over here on the left, but it's being stretched to the right, right? All these values that are stretching to the right, and this is, the center is over here, but it's being stretched to the left. So here's the same thing. If we kind of imagine drawing this curve over, right? we're stretching it to the left. So this is a skewed left distribution. Meaning the mean is less than the median. Okay. The center of the data set is around, the 70 to 74 mark. This is kind of the center of the data set. It's over here. Right, that's what we can kind of observe for this point, okay? So there's no real context. The context is the scores, but the skewed left, center of the data is around 70-74 mark, and the mean would be less than the median because it's skewed left. That's another thing I'll add here. So if it's skewed right, that means the mean is greater than the median. If it's skewed left, the mean is less than the median. Okay. All right. All right. Let's do the last section here. So this is not univariate anymore. This is bivariate. So for bivariate, we are going to be given a data set, and we have to find the least square regression line. Okay, so we got a fish market. We got the length and the weight. It's right here. And we need to come up with a regression equation. And that's going to be down here. Okay, so what is the explanatory variable? What is the response variable? What is it reasonable to predict that there could be both correlation and causation? So explanatory is going to be length. And weight is response. It makes sense that there's both correlation and causation because length will impact weight. Okay, makes sense, right? The bigger the fish is, like, the more it's going to weigh, right? Okay. So least square regression line. If you're watching the video, try to do it yourself, and then watch me. Okay, but here I'm going to do it. So pause the video if you want to try it by yourself. So you're going to go to stat. You're going to go to edit. We're going to clear these columns. Clear L1, L2, L3. And then we're going to put it in. So we got 8.5, 14.3, 16.8, 21.3, 23.3, 28.2, 30.8, 33, 34.9, 37.1. In the same order, 8, 38, 69, 148, 190, 318, 318, 455, 518, 651, 726. Let me take a second just to make sure I got it 100% right. So let's see, 8, 38, 69, 148, 190, 318, 455, 518, 651, 6. So that was good. 8.5, 14.3, 60.8, 21.3, 23.3, 28.2, 30.8, 33, 34.9. So yeah, good. So I got it. So just, you want to make sure you got it all right. We're going to stat, we're going to calc, we're going to lin reg, L1, L2. We're going to store that. So it's going to be alpha trace y1. We're going to put that for y1. We're going to calculate. And then here's my regression equation. So I'll make this clear on the test, but let's do 3 decimals. So we are going to have that the predicted y value is going to be 26.281 x minus 340.189. Okay, that's the least square regression line. So what does this mean in the context of the question? This is where the sentence frame comes in. This means for each centimeter increase in length, the fish's predicted weight increases by 26.281 grams. Okay? For each centimeter increase in length, the fish's predicted weight increases by 26.281 grams. The y-intercept means when the fish's length is 0 centimeters, its weight, predicted weight, don't forget that, predicted weight is negative 340.189 grams. R squared value, we got 0.9, it was roughly 0.920. So this means that 92% of the variation in fish weight is determined by fish length. And that makes sense, right? It makes sense, right? So, you know, the length of a fish is going to have a big impact on the weight. That's what this is saying. 92% of the variation in the fish weight is determined by the fish length. Okay, we have to go up here and do the residual and the predictions. So to get those from the calculator really easily, you are actually going to go to second table. Okay, so let me show you this. First, I'm just going to clear this, guys. Oh my goodness. Here we go. So I'm going to clear this table. I'll show you from scratch. So basically, my regression equation is already in here because I stored it earlier. If I go to second table, you'll get this. If yours does not look like this, it looks kind of funny. Go to second table set and make sure independent set to ask. Okay? So now I'll go back to table, and I can plug in all these values in and get the predicted weight, because this is plugging it into the regression equation, so I can get my predictions from here. So we got 8.5, 14.3, same, I'm putting all those x values in. 16.8, 21.3, 23.3, 28.2, 30.8, 33, 34.9, 37.1. Okay, so if we just copy those down, so I'm going to do here, so negative 116.8, 35 point, let's do one decimal, is fine, 101.3, 219.6, 400.9. Oh, I think I got off slightly here. Sorry, this is 272.15, 400.9, 469.3, 527.1, 577, and 634.8. Okay. The residual, so you couldn't find the residual by doing the actual minus predicted, and just you could do all those differences. You can also get it from the stat edit. If you go to L3 here, so go to stat edit L3, you can do that. You're gonna go second stat and then resid, enter, and that'll give you all the residual values. So I don't need to do each of those calculations. I can just copy down these values. So 124.8, 2.37, negative 32.3, negative 71.6, negative 82.2, negative 82.9,
negative 14.3, negative 9.1, 73, 74, then 91.2.
Right, so those are all the residuals. Last page now. Now it's asking us for a residual plot. Okay. While I'm at this, I can do E really quickly while I'm on the table. I'll come back to B in a second. But for E, if you go to your table, this is not the stat table, but the prediction table where it's like second graph. You put in 2. That's the predicted weight, negative 287.6 of a fish that's 2 centimeters long. Okay. So this is the idea that when you have a least square regression line, like this one, the predictions are often decent within the data set, but then start to lose it a bit as you go beyond the center of the data, right? So at the edge of the data here, we're losing it. Down here, we're getting some negative values, so it's not that good. In fact, by looking at this, you can kind of see it's not exactly perfect. Even though it looks okay, I think we could get a better model here, right? And what we'll do here now, I'm gonna do B here. So what I'm gonna do is I'm gonna plot the residual. Okay, so the residual is in L3. I'm gonna do a stat plot. I'm gonna do L3 here. I'm gonna do zoom 9. And this, we can ignore this. Now we can turn that off. Don't worry about that. That's not part of it. This is our residual plot. So, and this was really clear by the graph I just showed you. This is not good. The way that this shape is, this is not good for linear, because this is showing that there's a curve to the data, a distinct curve. It's not a straight line. It's curved. Okay, so we can plot it. If you look at trace, you can get those points. So we got 8.5, 124. It doesn't have to be perfect, guys. And then 14.3 right here. It's very small. Right here. Right here. Another point here. Another point here. Another point here. 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 So even though the R squared is good, so like, that R squared is pretty good. It's in the 90s. And the linear model is doing okay. It's not the best fit for our data because our data is not it's really not linear. We have basically, again, we have a bunch of here you're getting these underestimates, then there's a bunch of overestimates, there's some underestimates. And that is made clear by this. If we graph the original for a second, here's L2, zoom 9, and I turn on that graph again. That's what we're seeing here. Underestimate, overestimate, underestimate. And that's because the line is what? The line is curved. Really a polynomial or an exponential would be a lot better model here.
And we didn't get to that in the class, but that's what you do, right? You can do see under stat, under like quad regression, cubic regression, chord regression, ln regression, exponential regression, power regression. Like, these are all other kinds of regressions that you can do. We only dealt with linear because it's the kind of the introductory one, but this is not a good case for linear. So because there is a distinct pattern to residual plot, it is not a good fit. Okay. All right, down here, we're just labeling which one of these matches here. This is pretty straightforward. So 0.76, that's got to be D. 0.22, it's got to be B. I think it's 0.49, it's got to be C. And then negative 7.74 has got to be A. So like, the closer it is to like a line, the closer it is to 1. And if it's negative, it's going down. If it's positive, it's going up. Okay, that is the practice quiz. That is the review. Good luck, guys, and I will see you soon.